Hello everyone and welcome back. Now, I would like to pick up this lecture directly where we left off in the last one. So if you haven't watched the last video, go back and learn about Koopman autoencoder neural networks. Because I want to focus on a tiny detail that I kind of swept under the rug in the previous video. And that was the size of the latent dimension, right? The number of Koopman eigenfunctions you're going to use. Now, I did the application or the demonstration on a very simple system that I knew I could get away with 3. But I also told you at the end of the video that in practice, this number is a hyperparameter for the neural network. You need to typically take it very, very large. There are applications with Komodo-Shibashinsky that require it to be, say, 128 dimensional, and there are applications where it's even larger than that sometimes. So this becomes a problem sometimes because you might ask yourself, well, what should I choose? Do I just have to sweep over numbers? Do I just keep taking bigger and bigger latent dimensions? And in practice, the answer is yes. Typically, the bigger, the better, but there is no prescription. But I want to talk about today a single application of Koopman autoencoder neural networks where we know the exact size of the latent dimension, and that's because it is related to an area of classical mechanics. So we're talking about Newton, Hamiltonian, Louisville, all of these very famous people who worked on classical mechanics and were able to derive things like action angle coordinates. So what we're going to do is connect a very old concept and a very classical concept of action angle coordinates and integrable dynamical systems to the neural network world, sort of bringing things together, sort of looking backwards in order to look forwards. Okay, so if we are going to talk about action angle coordinates, that means that we're going to start by talking about Hamiltonian dynamics. Okay, so if we have a Hamiltonian function, now maybe there's some people that are going to watch this and they're going to be disappointed that I'm not going to do this in full generality, right? If you're coming at this from sort of modern mathematical physics, you're used to talking about these things on manifolds, compact, non-compact manifolds, all this kind of fun stuff. For me, I'm going to keep it really simple. I'm going to talk about a Hamiltonian function. So typically this is what we call the energy, right? This sort of abstract concept of the energy in physics. I'm just going to talk about it from a even dimensional space into the real numbers. So again, this is the real number that I output here is the energy. And I'm going to talk about Hamiltonian dynamics. The dynamical system associated to this is going to be written in this form. Now I just need to make sure I have this right. Yes. P and then P and Q. And then P dot is equal to minus H, right, Q, P, comma, Q. Now, these things are called, the Q is the generalized momentum, P is the generalized position of your particle or whatever it happens to be. They're both of the same dimension here. So this is an example of what's called a conservative system. It means that solutions, so we know this, we know solutions satisfy H of P of t, Q of t is equal to some constant for all time. Okay, that means that energy, for example, is conserved in the system. There is no energy being put in or out. Whatever the amount of energy is that you start with, that's the amount of energy you maintain, right? So this is a conservation law. And in fact, we would say that this system is integrable. Okay, so we would call this thing integrable if there exists, so integrable, if there exists f1 through, I believe it's fd, let me double check that, yes, fd, which are going to be other conserved quantities. One of them will be the Hamiltonian, and then you'll have d minus 1 other ones, such that, so conserved quantities, Now we saw that conserved quantities, these things, if we bring this back to Koopman for a second, conserved quantities are in this case, because we have continuous time, they're eigenfunctions of the Koopman operator with eigenvalue 0. If it's discrete time, then they have eigenvalue 1. Remember, we learned a little bit about this when we talked about discovering conserved quantities. And we know because these things are eigenfunctions, they have, they can be added together in linear combinations to produce new ones. So what we want to have is sort of d-linearly independent eigenfunctions. The way that, or conserved quantities, the way that we do this is through what's called the Lie bracket. So I'm going to use these curly brackets. So fi comma fj is equal to 0. Or sorry, the Poisson bracket, pardon me, for I not equal to j. And then this Poisson bracket looks like this. Okay, so it takes this form. F and G in this thing is going to be the summation over all of the variables. So J equal 1 to D. And then let's say partial of F with respect to Qj, so the jth component of Q, times partial G with respect to the jth component of P, and then minus partial F, and then this is with respect to Pj. All right, so it's a little bit of accounting. Now, you can just go back and check that this is that this itself is actually just going to give you a conserved quantity. You can show that this in fact does give you the conserved quantity relationship here with the right-hand side. And that this is, I'm going to leave it as a little bit of homework for you, but this is actually directly related to what we get out of the Koopman framework whenever G is equal to the Hamiltonian, okay? And that's because of this right-hand side relationship. But here's the point, okay? So if we have a bunch of conserved quantities, we know, for example, what we know about conserved quantities is that solutions are confined to their level sets. That's exactly what this conservation law right here says. So the more conserved quantities we have, the more restrictions we have on the dynamics, right? We saw this with discovering conserved quantities. We saw that we had to rely on intersections of these things. Now here's the point. I have d variables. I have d conserved quantities. That means that the solutions to this thing are completely uniquely defined as the intersections of all of these conserved quantities, okay? And that's why we call it integrable, okay? Because it says wherever you start, there is only one trajectory with a complete, everything is completely prescribed by where you started on these in these intersections. And we can go a little bit further here. We can introduce, okay, so I said I wasn't going to talk about manifolds. Here I am talking about manifolds. We're going to look at the set of all P and Q in two-dimensional or even-dimensional space such that Fj of P comma Q. So we're going to look at level sets of each one of these things, j equal 1 to d, for this integrable system. So this thing defines a manifold. It's just an intersection of all of these level sets, okay? Now, there's a very famous theorem called the Liouville-Arnold theorem. So again, two very famous people in classical mechanics. Arnold, just a giant of dynamical systems. There are many, many things named after him, not just the Liouville-Arnold theorem. He wrote some fantastic textbooks. I mean, this is really one of the sort of gods of dynamical systems. But basically what they said is if this thing is compact, okay, if it's compact, then it's basically a torus. So this is what they prove, essentially, okay? Now, I'm obviously sort of generalizing this. You need a few more specifics, but here's the point. If you're confined to a bunch of level sets that can't really go anywhere, then they just sort of roll back on each other. So this is just a d-dimensional torus, essentially. And what it says is that there exists a coordinate system, okay, on that torus, which we call action angle coordinates. So coordinate system. And I'm going to sort of skip a little bit of the details. I mean, the Wikipedia page on action angle coordinates is fantastic. But basically, what it does, here's the loose description of what action angle coordinates do. Let's take a look. Here's my beautiful torus, right? I should be an art major with that thing. Basically, you have one dimension for rotations in this direction, and then you've got another one, right? So we know that a torus, for example, my two-dimensional torus here is parameterized by two frequencies, okay? But in this case, we also have two radii. So one radii is the radius of the sort of horizontal circle. I'm going to call that I1. And then there is another radii, which if I do it like this, it is the radius of the second circle. And effectively what we get here is that the new coordinate system just parameterizes every single one of these tori to look like this. I, the derivative of this thing is equal to 0. So each one of the radii is fixed in time. It's prescribed by wherever you started. The one way to imagine this thing is the i's give you bigger or smaller tori in each direction, and they are prescribed by your initial conditions. And then the theta is the sort of movement around the torus. And so the theta k components are actually given just by some frequency of movement that is prescribed by what you started with in these I coordinates. So these are called action angle coordinates, okay? So this is the action, and then as you can probably guess, this is the angle coordinate. So essentially it says the initial conditions describe the size of the torus, and then the size of the torus prescribes the frequency of motion, because you can see that the solution to this thing, right? So the solution is given by ik of t is equal to ik of 0 for all t. That's easy, right? Because the derivative is equal to 0. It's a constant. And theta k of t is equal to omega k, frequency, and then times whatever these things were initialized as, ik of 0, times t. So it's just usual sort of movement around the circle, constant angular momentum, and then plus whatever the initial condition was as well, right? So that's just the initial offset. Doesn't do anything all that interesting. Okay, so there's your crash course in classical dynamics, everybody, right? Now you've learned everything you need to know about mathematical physics. Obviously, that's a joke. But how does this relate to Koopman, right? Well, let's take a look at something. Okay, so these are basically polar coordinates for maybe the complex plane, for example, right? So each k value, this describes a radius, and this describes an angle. So then what you can do is we could define, let's say, psi sub k of p and q. Remember, these things are coordinate changes from the original system in p and q, right? So if I was able to say where I started in p and q, I could follow that coordinate change. I could figure out what these initial conditions are as well. And so therefore, I could write it like this. Sorry, this should be a k. E to the I theta k of p and q. And what I'm doing here is just emphasizing, because this is a coordinate change, they depend on the original variables p and q. And in fact, it's an invertible transformation. So it means that if I started with I and theta, I could go back to the p and q coordinates, at least locally. And so in particular, right, these things effectively become Koopman eigenfunctions, okay? And so the reason for that is because if I look at the dynamics, right? So if I look at solutions, p of t and q of t, then what I can see here is that phi k, p of t, q of t, if I just put the solutions into this thing, well, this just becomes e to the I omega k, and then all of the initial conditions. I'm not going to write them again just because it's a lot of writing for me. And then times t, and then multiplied by the original initial condition. K, p of 0, q of 0. Now what is that? That is a Koopman eigenfunction, right? If we did this in discrete time, if t was just some tiny little step forward into the future, say h, then it would tell me that the eigenvalues of the discrete time Koopman operator are just e to the I omega times h, right? If I know how I start, then if I want to go forward in time, it's just multiplying by an eigenvalue. That means, okay, what all this means is that action angle coordinates naturally give you eigenfunctions of the Koopman operator. But here's the weird thing. They're parameterized by where you started, right? So, in fact, it's a little bit messier. And what I mean by that is the eigenfunctions, they vary based on where you are in space. And in particular, the eigenvalue varies based on where you are in space, because there it is right there. Where I am in space determines the frequency of oscillation. So if I want to set this up as a neural network, I would like to take data from an integrable system, and I would like to learn the linear representation, which again is the same dimension. It's, well, this is complex, d-dimensional. Complex is 2 dimensions, or double the number of dimensions for real. So this is 2D dimensional, because it's no longer, if we make it real. 2D dimensional, 2D dimensional. Okay, so don't have to determine what size of latent space I want. Fully linear representation of the dynamics in the action angle coordinates. The only problem is you have what's called a continuous spectrum. The eigenvalues here depend on where you are in space. They are fixed by your initial condition. And so what we are going to do is we're going to build an auxiliary neural network. So an auxiliary neural network, I'm going to call it capital Omega, okay? And capital Omega, because everything lies on a circle inside of the neural network, right? Then if you think about that setup, that Koopman autoencoder network that I had last time, where data goes in, it gets transformed according to the Koopman eigenfunctions. You identify the Koopman eigenfunctions. Well, if you call the latent space elements y1, y2 for the real and imaginary parts of the first component, y3, y4 for the real and imaginary, so on and so forth. So again, using the same notation, my auxiliary neural network is going to only depend on the radius of the circle that you are on inside the neural network. And I'll show you how this works in a minute. And then all the way up to y2d minus 1 squared plus y2d squared, and which is equal to, and then the output of this thing is going to be, it's going to learn the frequencies, right? So it's going to be omega 1 of I1 of 0, ID of 0, and then all the way down to WD. So basically what you do is you create another neural network that sort of sits along with the original Koopman autoencoder network that learns the frequencies depending on where you start or what circle you are on. Let me show you an application of this so you can really understand it. So I want to do my demonstration on the Kepler system. Okay, so this is a 2-dimensional ordinary differential equation. The reason for that is because this is a second-order model. Okay, so if you turn it into a first-order model by splitting it up, maybe R and S variables or something like that, essentially this is a 2-body problem. Okay, so R represents the distance between the 2 orbiting bodies. You can see that there is one steady state in this system at R equal to 1. So I've scaled all the variables so that when these 2 bodies are exactly 1 unit apart from each other, they maintain a constant distance and keep rotating each other. Okay, that's represented in this top picture here by the blue dot. Okay, now when r is away from 1, essentially what happens is, 1 is orbiting, it gets closer, and then it gets further away, right? So sort of how the Earth orbits the sun. And the further away it starts, then the more dramatic this orbit's going to be. These are the periodic solutions you're seeing in this r dot plane at the top of this picture here beside me. So what I've done is I've trained up a neural network that takes in data across all of these periodic solutions, and it performs a transformation of these action angle coordinates to learn a perfect linearization of the system. So the perfect linearization is in the bottom corner here. You can see it right here. Here is that steady state that was the perfect orbit. It's been mapped into 0. The red orbit here has been mapped into the red orbit here. You can see that these are perfect sinusoidal oscillations. The only difference is that each one of those periodic solutions has a different frequency. And this is where the auxiliary neural network comes in, which is shown over here, where I have omega, which identifies the frequency based on the radius of the circle in the latent dynamical system, right? So here you can see that the action angle coordinates lead to this linear dynamical system, again put into real coordinates instead of complex coordinates, where you're sort of advancing according to this rotation matrix, and the frequency of that rotation is selected by this auxiliary neural network. So what you can see is there's basically a linear relationship. It's a really simple system. Basically, the further you get away from that perfect rotational solution here, that steady state at r equal to 1, you sort of decrease the frequency as you get further and further away. In the periodic solutions, the period is longer and longer. So how is it that I programmed this up? Well, I actually had some help from a very good friend of mine named Bethany Lush, who is an excellent machine learning expert at Argonne National Laboratory. So she actually helped me code this because she is much better at neural networks than I am. And basically what you can see here, okay, so we are going to gather data from the Kepler experiment. So again, I'm going to simulate up a whole bunch of trajectories, just short bursts of trajectories along all of these little periodic orbits, right? Because I need lots and lots of data here, because each trajectory is confined to a level set. I need to go over lots of level sets to get lots of information. I'm going to then go in and train up my neural networks here. So here's some of my data that I'm going to put in. This is the Kepler system. This was this guy right up here, right? This is my cartoony, a little bit more dramatic picture. Here's what the actual data looks like. Every single one of those colored curves is a different trajectory of the system. Here, I'm just going to show you the training validation and the loss on the validation data and the training data. You can see these things are very, very small. This was a very good run. But again, you can try and run this yourself. Download the code from my GitHub. Try this. Try it on a different system. Try it on the pendulum, for example. It's another system where this will work very well. Here, we're sort of just training the loss. Not a very interesting picture. But here's that omega function coming out. So you can see some gaps. This is maybe where a little bit of data was missing. But of course, we can interpolate this thing. It's a nice sort of straight linear relationship. And here is the projection to the linear coordinate system. Again, this is what I was plotting right in here. Now, of course, this is a relatively simple example because it's a planar dynamical system. We know that any Hamiltonian system that is two-dimensional is immediately integrable. For higher dimensional systems, then your omega function needs to be it needs to be an argument of d dimensions. So if you have a four-dimensional integrable system, then your omega function goes from 2 dimensions up to 1 or down to 1 dimension to determine the frequency of the oscillation. So there's some complexities here. Of course, the decoder neural network, something I didn't mention, also needs to be nonlinear to transform you out, and that's because you're going from the same size of space. These aren't the transformation that gets you into action angle is nonlinear, and so the inverse of that is also nonlinear. So that is one piece of this that is a slight complexity over what we saw with the autoencoder neural networks. But the beauty of action angle coordinates is that we do not have to figure out the size of the latent dimension. We already know it. It's the same size as the system. We're just trying to learn these coordinate transformations. topological conjugacies, everybody, right? Autoencoders, topological conjugacies, the best of friends you can have in dynamical systems. When we come back in the next video, we are going to talk about the last lecture in this whole series where we take autoencoders, we take Cindy, and we put them together in order to find optimal reduced order models from data. So I'll see you all in the next video, everyone.